One last video in this section, and what we're going to do here is find the pH of a solution that contains a weak base. In this problem, we're told that we have a 0.2 molar solution of ammonia, and we need to find the pH. We should begin by asking ourselves what type of a problem we're dealing with here. And to get the answer to that question, we have to figure out what type of a substance NH3 is. So you can take a look at the table of acids and bases, and what we find is that NH3 appears here in the A- column. And I'll again remind you that when we're talking about bases, the only strong base that we have is hydroxide. All the other bases that we have on the table are either weak bases or ineffective bases. Since NH3 is the conjugate base of a weak acid, NH3 is itself a weak base. Therefore, we can say NH3 is a weak base, and when you have a weak base reacting with water, you're dealing with an equilibrium problem. I'll remind you that we're putting all the eek sounds together, right? Weak acid, weak base means equilibrium. Now, in this problem, when we're told that the concentration of ammonia is 0.2 molar, that's indicating the initial concentration of ammonia. And when you're finding the pH, the pOH, concentration of H+, concentration of hydroxide, that's referring to the equilibrium concentration. Therefore, we have to connect the initial and the equilibrium state here. We know initial conditions, and we need to find equilibrium conditions. Therefore, we will need to make an ice table to solve this problem. Before we begin doing that, it's also beneficial for us to predict what a reasonable answer would be in this problem. So since this is a solution that contains a weak base in water, what we can say is that we would predict that the solution is basic. So we could predict that the pH has to be a number greater than 7. Therefore, if at any point in this problem you're seeing something that's less than 7, it either tells you that you've made a mistake or it tells you that you're not done with the problem yet. It's just a good way for you to keep focused on what a reasonable answer is. Let's now set up the ice table problem. So to do that, we need to first write the reaction that occurs, and we've looked at this reaction before for the dissociation of NH3 in water. Both are weak, so this is an equilibrium reaction, and the products we've talked about before are going to be NH4+ and the hydroxide ion. Furthermore, whenever you have an equilibrium problem, you want to be thinking about the K for the reaction, right? Think about what equilibrium constant is controlling the equilibrium state that you have here. And in this problem, because we make hydroxide ion, we're dealing with a Kb. So if you see the hydroxide ion on the right-hand side of the equation, you're dealing with a Kb. We can write the Kb expression for this reaction. Kb is the concentration of NH4+ times the concentration of hydroxide ion over the concentration of NH3. Additionally, we should know what the value of Kb is. And the table doesn't tell us that, but it does tell us the Ka of NH4+. So let's get that value. So the Kb is going to be 10 to the minus 14 over the Ka of NH4+. Therefore, the Kb is 10 to the minus 14 over 5.6 times 10 to the minus 10. That is 1.8 times 10 to the minus 5. Now, let's set up the rest of the ice table. So make our initial change in equilibrium lines, and we're told that the initial concentration of NH3 is 0.2 molar. We don't care about water because that's a liquid. It doesn't appear in the K expression, and the amount of water has no bearing on what the pH of the solution is. Initially, we'll say that there's no NH4+ and no hydroxide ion present. Therefore, this reaction has to progress to the right. We're going to make some hydroxide, we're going to make some NH4+, and we have to use up some of the NH3 in order to do that. We add the initial and the change lines to get the equilibrium line. 0.2 minus X for the NH3, X for the NH4+, X for the hydroxide ion. And because the value of Kb is quite small, it's less than 10 to the minus 3, you can use the small x approximation to help solve this problem and to avoid the quadratic equation. So approximate the concentration of NH3 at equilibrium to just be 0.2. Now that you have the equilibrium line filled in, you could take everything that's on the equilibrium line and you can plug it into the Kb expression. So plug everything into Kb. Now, we have that Kb is 1.8 times 10 to the minus 5, and that's also equal to the concentration of NH4 plus at equilibrium, which is X, the concentration of hydroxide at equilibrium, which is also X, over the concentration of NH3 at equilibrium, which we approximated to be 0.2. Now, multiply both sides by the 0.2, and so you'll have on the left-hand side of the equation 3.6 times 10 to the minus 6 equal to the right-hand side of the equation, x times x squared. To solve for x, take the square root of both sides of the equation and get that x is equal to 0.0019. Now, anytime you find the value of x, it's important, it's really crucial that you then go back up to the ICE table and figure out what that value of x means. So the value of x represents the concentration of hydroxide ion. So let's write that out. What we found when we got the value of x is the concentration of hydroxide ion. That is 0.0019 molar. Once you have the concentration of hydroxide ion, you can find what the pOH of the solution is by taking the negative log. And when you plug that into your calculator, you'll find that the pOH of this solution comes out to 2.7. It would be really tempting at this point to say, here's a number, 2.7, I took a negative log, maybe I'm done with the problem. But it's so important for you to think carefully about what you've just found and whether or not it's a reasonable answer. So first and foremost, because you've been labeling things throughout the problem, you know that you haven't found the pH, you've found the pOH. And additionally, at the outset of this problem, we said that we would predict a final answer that is greater than 7. This is not a number greater than 7, and so we're not done with the problem yet. We know there's another step that needs to be done. We have to now convert the pOH into a pH. So the last thing for us to do is to say that the pH plus the pOH equals 14. So the pH is 14 minus the pOH. 14 minus 2.7 is 11.3. That is the pH of the solution, and that's a number that makes sense. You would expect there to be a pH greater than 7 if you're dealing with a solution that contains a base. That brings us to the end of this video in this section. Next, we'll talk about acid-base properties of salts and calculating the pHs of solutions that contain salts.